Hi everyone, I'm Thiago Lar, I'm a stroke neurologist from Brazil, and I will present the article that is related to UNET, a convolutional neural network designed specifically for biomedical image segmentation. This model was introduced by Honeberg and Fischer and Bronx in 2015. They are from the University of Freiburg, and this model has become one of the most widely used architectures in medical AI, including my field, neurology, largely to its simplicity and effectiveness. As for the background, accurate segmentation is crucial in medical imaging, whether it's for detecting tumors, segmenting organs, analyzing cells, or even in the stroke care, as in my case. However, manual annotation is low subjective and often inconsistent, as in this case we use a 3D slicer to manually segmentate the image, but of course this depends on the capacity, the training of the specialist, and it's very hard working too. Traditional convolutional neural networks struggle when training data is limited, which is often the case in medical contexts. So, UNet was designed specifically to enable high accuracy predictions even when with very small data sets, addressing this common challenge in biomedical applications. As for the architecture, it is shaped like a U, and that's why the name, and with a contracting path on the left and an expanded path on the right. The contracting path learns context, while expanding path restores spatial resolution. A key innovation is the use of skip connections that copy feature maps from the contracting side and concatenate them with upsampled features. This helps the network retain precise location. In more detail, the contracting path repeatedly applies 3 by 3 convolutions, followed by ReLU activations and 2 by 2 by 2 max pooling for downsampling. This path compresses the spatial dimensions with capturing increasingly abstract representations. The idea here is to gather contextual information necessary for identifying structures in the image. Now, the expanding path performs up convolutions and transposed convolutions to upsample the feature map. At each level, it also concatenates the corresponding feature maps from the contracting path. These skip connections allow the model to combine context with fine-grained location, which is essential in medical segmentation where precision matters. Since biomedical data sets are often small, data augmentation is key strategy to prevent overfitting and improve generalization. This slide shows common augmentation techniques using in training deep learning models for medical image segmentation, such as rotations and flips, which help the model learn invariance to orientation, translation and shearing, and also scaling, which simulate different anatomical positions and sizes, adding noise to simulation acquisition variability, and adjusting brightness to mimic scanner differences. These augmentations are applied both to the original image and their corresponding segmentation mask to maintain label assignment. Beyond the standard augmentations, elastic deformations are especially powerful in medical imaging too. They simulate more realistic anatomical variability, such as changes in tissue structure due to pathology or motion artifacts. Uh, Here we see an original image followed by a grid distortion and an elastic transformation. These deformations stretch and bend the image grid, mimicking natural variability while preserving anatomical plausibility. Elastic deformation were particularly emphasized in the UNET paper and helped achieve better generalization with very few training samples. Another key training strategy is the design of the loss function, especially in the context of class imbalance. In medical images, pathological regions like tumors, lesions, stroke are often much smaller than the background. If not handled properly, the model may ignore these small but clinically important areas. The UNet model uses pixel-wise softmax combined with weight cross entropy, giving more importance to underrepresented classes and focusing on the borders of the regions. This figure from Huang et al. Shows how different loss functions influence segmentation performance, particularly for small and overlapping tumor regions in this case, but it can be applied in other conditions. Hybrid and dice-based losses help the model identify more accurately and complete tumor boundaries in this case. Uh, as for results and applications, the UNet achieved state-of-art results when retrospectively tested on benchmark datasets, including the ISBI 2012 Electron Microscopy Segmentation Challenge and the ISBI Cell Tracking Challenge. While we didn't participate in those challenges at the time, as the UNet model was created in 2015, it outperformed the originally submitted methods, demonstrating impressive generalization from very limited training data. What's truly remarkable is its broad adoption across fields like neurology with MRI CT, also histopathology, and its impact on the development of successors like NNUNet and TransUNet, which are now staples in the modern medical image analysis. Here's an example that I applied during my PhD thesis. We developed AI models to distinguish hemorrhagic transformation from contrast extravasation on CT of patients with ischemic stroke that underwent thrombectomy within 6 hours. Well, thrombectomy is a very efficient treatment in medicine, in the stroke care, but it can increase the risk of hemorrhagic transformation, which increases a lot the risk of mortality and disability. But in the first hours, it's very difficult to differentiate them. Both of them appear hyperdense, as in this figure, it is hyperdense in 24 hours, before 24 hours. And if the hyperdensity remains, this is blood, then hemorrhagic transformation. And if the hyperdensity wash out, then it's contrast, a more benign feature. But usually you need to wait up to 72 hours to make this differentiation. So we trained a UNet model with just 111 cases to differentiate these cases of hemorrhagic transformation and contrast extravasation. We compared radiomic-based classifiers such as support vector machine, random forest, logistic regression with the UNet deep learning model. And the UNet model achieved the best performance with 96 accuracy and area under curve above 0.98, which is truly impressive. And this approach can improve early decision making for stroke neurologists. As for conclusion, UNet revolutionized biomedical image segmentation by making feasible with small annotated datasets. Its key strengths lie in combining contextual understanding with precise locations. Thanks to its symmetric architecture and skip connections, uh, it's a landmark model that continues to inspire new developments in medical AI and also in my field, that's stroke care. These are the reference. Many thanks.